Hello class. So in the last class we have discussed about DFT. Introduction. We have given an introduction to DFT. So what was DFT? The definition of DFT was the symbolic representation is capital X of K is equal to n going from 0 to capital N minus 1 x of n w n to the power kn, where k goes from 0 to n minus 1. Again, the IDFT was x of n is equal to 1 by capital N summation k going from 0 to n minus 1 capital X of k wn minus kn, where n goes from 0 to n minus 1. See, in both the cases, whether it is DFT or IDFT, if you notice, there are two variables changing from 0 to n minus capital N minus 1. Both n and k are changing from 0 to n capital N minus 1. See, this is the difficulty of solving DFT. This makes DFT a bit time consuming because you have to consider two variables changing at the same time. So this creates a problem. We will be solving problems regarding DFT, and I will tell you how to handle this situation, how to handle the two variables changing at the same time. Now, one more point I would like to draw your attention to, that here if we see wn to the power kn, in the small n, the power of wn, there is a small n. If I add a capital N with this, if I add a capital N with this, then what happens? Is there any change in the value? If I add a capital N to this Tudor factor, in the power of Tudor factor, if I add a capital N, no, there isn't any change due to because wn is e to the power minus j twice pi by n. If I add a plus n, that means we are actually adding twice pi with cos and sine. Cos and sine retains its value, its original value, if I add or subtract with a multiple of twice pi. So because of the characteristics of cos and sine, because we can write e to the power minus j theta as cos and sine, it doesn't change. Wn to the power kn or wn to the power minus kn doesn't change its value if I add a capital N to it. You can do the problem and see it won't change because of the characteristics of sine and cos. Sine and cos doesn't change its value if we add theta with a multiple of, add or subtract it with a multiple of twice pi. So we can say that xk and both xk and x of n, capital X of k and small x of n, are periodic with period capital N. That means capital X of k repeats itself after every n in both the directions. Similarly, small x of n also is periodic with period capital N, and it will repeat itself after every n period in both the directions. So what do we conclude from here? We conclude that in DFT, our band of vision or our concern, area of concern, should always be from 0 to n minus 1, because it will repeat itself after every n times. So this is the first conclusion that we can draw from here. And here we can notice another thing. See, we haven't started with a periodic xn. Xn was a finite sequence, but of course not periodic or may be periodic, but you cannot it or we can say it was finite, but periodicity was not there. Periodicity was not a criteria, but finite was a criteria, isn't it? It was finite sequence. I have stated that DTFT holds for both finite and infinite sequence, but DFT holds for finite sequence. It will have a length of capital N. But here, what has DTFT done to XN? After DTFT, we see that XN has been made periodic, which was previously not periodic, which was previously finite but aperiodic. But here we have made XN periodic. So what is the result? It has both advantages and disadvantages. Disadvantages, it has changed the signal XN. Previously, which was finite, is now changed into a periodic signal, which we have actually changed the signal. This is a disadvantage. But what is the advantage? Advantage is this has been seen, or within the range of 0 to n minus 1, there will never be any aliasing. Aliasing is removed in this range. This is the advantage, because after every n times it is repeating itself. So it is in this range of 0 to n minus 1, there is no aliasing seen. So in DTFT, from now onwards, our band of vision is strictly maintained from 0 to capital N minus 1. We will never allow anything in DFT to go beyond this range in either of the directions. So this is a mandatory criteria. Now we move to the next slide from where we have left. So we have left in the circular shift criteria. So what does circular shift mean? Previously, in all the other transformation methods, we have seen the second criteria or second property was time shift. Here we have removed the term time shift. We have brought into a new term called circular shift. So what does this phenomena mean? Before going to the property, we need to know what this phenomena is. Circular shift, as the name suggests, is the shift going on in a circular manner. For example, whenever there is a shift in the sequence, a vacancy will be created. Fine. Previously in time shift, what was happening? Whenever there was a shift, say for example x of n minus 1, it was shifted and it was in a line, in a straight line. The shift was in a straight line. For example, if you have a sequence of length 4, that is from 0 to 3, whenever you have a shift of minus 1, you will have the signal moving from x of 1 to x of 4. X of z at n is equal to 0, there is a vacancy created. And the signal has moved to x of 4. But there is a constraint in DFT. We cannot allow anything to move out of our range of vision, which is 0 to capital N minus 1. That is in our case for a length of 4, that is capital N being 4, our band of vision is strictly limited to 0 to 3. We cannot allow x of 4. Argument of x can never be 4. This is violating our band of vision. So what we do, we consider it as a loop or a circular path. Previously, which was a straight path, straight line, is now a circular path. What will happen to x of 4? It will not be x of 4. Actually, x of 3 will have a circular shift and come over to x of 0. That is, a circle is created. It, instead of going to x of 4, it will come and take the vacant position which is being created. That is, x of 3 will not move to x of 4, it will come to x of 0, a circular shift. Similarly, if it is x of n minus 2, x of 3 will come and take the position of x of 1, and x of 2 will come and take the position of x of 0. Everything in circle. That is why it is called circular shift, not time shift. And if you see the property, it states g of n minus n naught modulus n. Now what this modulus n suggests, previously you haven't seen this pattern any time. This is a new thing, modulus of capital N. This is called modulus of capital N. Previously, every time you have written g or x of n minus n naught, n minus x, n minus 1, n minus 2, anything. But no modulus. Here the term modulus of capital N has taken place. Previously, I have told you about the physical interpretation of the term circular shift, how physically the shift is going, but how mathematically do you explain it, or what takes care of the phenomena that x of 4 will not exist, x of 3 will come to x of 0. What takes care of the phenomena that the shift or whatever operation we do is argument of x can never be out of our range. This is being taken care by the modulus n. What does this modulus n mathematically do? Whenever we are seeing that the argument of x is going out of the way, out of our limit, out of our band of vision, this modulus n will be either added or subtracted from the argument of x, to either added or subtracted as the case is, to bring it back to our band of vision. Say our band of vision is 0 to 3. Now for one shift it is moving to x of 4. I told you x of 4 is not possible. Then what will you do? If I add plus 4 to it, because our length capital N is 4 in our case, if I add plus 4, what will happen? It will become x of 8. Again out of our vision. I told you, you have to either add or subtract as the case is to bring it back to our band of vision. Here we have to subtract. Whenever you subtract 4 from 4, what will happen? It will become x of 0. That means what? Our x3 is moving to x of 0. Now what will happen to, say for example, it was a plus shift, that is x of n plus 1. What would have happened? X of 0 would have moved to minus 1 point. Minus 1 is not allowed. So what we do? We add here plus 4. Adding plus 4 means x of 3. So what would happen? What would happen? Similarly, x of 0 would have moved to x of 3. No x of minus 1. x of 0 would have moved to x of 3. This is how circular shift works, and this is the mathematical representation of g of n minus n naught modulus capital N. And when we take its DFT, it is equal to Wn to the power k n naught into whole multiplied by g of k, same as DTFT. Same as DTFT. In DTFT, you wrote it in e to the power j term, and there was a negative sign which is being absorbed by Wn here. The proof is also the same. We will move to the next property in the next class. Thank you, class, for now.